We have observed here at Honeywell that approximately 30% of the TPA-100 processors that are removed in the field result in no fault found in the repair shops. So this implies that the processor was not the reason for removal, that there was some other system effect that contributed to it being flagged for maintenance. So we want to talk in this webinar about some of the operational aspects, various maintenance procedures, and some service bulletins that can be useful in impacting the TPA-100 No Fault Found removals. The TPA-100 processor is part of the TCAS system. You can see the TCAS system in the diagram includes two antennas, Mode S transponder, of course the processor, and then an array of display or control devices depending on your aircraft. The TPA-100 processor communicates with other aircraft, which we will refer to as intruders in this discussion. It's a common TCAS terminology for the other aircraft. It will determine the range, the bearing, and the altitude of the intruding aircraft, and from this it will calculate what we call the closure rate. Based on this calculated rate and a predicted miss distance, it will determine the appropriate threat level and, if required, generate the appropriate display information. TCAS is, of course, a collision avoidance system, but it is also effectively a communication system. And this is something commonly misunderstood about TCAS. TCAS is entirely dependent on communication with the transponders installed in other aircraft. You can see in the diagram, TCAS sends interrogations on the frequency of 1030 megahertz. They're received by the other aircraft's Mode S, which then replies on a frequency of 1090 megahertz. So based on the interrogation time and then the resulting reception of a reply, we're able to measure the distance of the other aircraft. We'll also look at the phase differences in the received signal, which will determine bearing. We'll talk more about that later. Also, there's a capability for TCAS to TCAS communication in the event of what we call the resolution advisory scenarios. In this case, the TCAS will send a message to the other aircraft's Mode S transponder on the 1030 megahertz frequency. The Mode S will see the contents of the message, and then on the internal AirInc 429 bus, it will forward that to the TCAS. TCAS will then acknowledge that with a transmission to the other Mode S transponder in the other aircraft, and it will, of course, be forwarded to the processor. So, again, this just gives us a snapshot that emphasizes how important the TCAS to Mode S communication is. So let's talk a little bit about how it works, or the function. In the diagram, we see a big area labeled surveillance volume, and this is the area that the TCAS processor is searching. It's monitoring this airspace. But I want you to think of this as the TCAS RF, or radio frequency range. This is the area that we're able to transmit interrogations throughout and then, of course, receive replies. As the TCAS searches this area, it acquires the other aircraft's position. As you can see, the blue aircraft there is the intruding aircraft. And we're going to calculate a time to the intruding aircraft's closest point of approach. Based on the closest point of approach, or the CPA value, if it's within certain limits, of course, a certain time duration, and then a certain miss distance, the TCAS processor will calculate the appropriate threat level. If the aircraft doesn't necessarily represent any threat, we may display it as a non-threat aircraft symbol. If we predict that it's going to come closer than we would like, and it is then declared a traffic advisory. And in this case, we change the traffic symbol to a yellow circle, and a audio alert traffic will be enunciated to the crew. If the situation continues to get worse and the aircraft closure rate continues to be within unacceptable boundaries, we may then generate a TCAS resolution advisory. This will change this color of the TCAS symbol to a red square, but it will also give us a guidance command, a vertical guidance command, so that we can achieve a safe separation. It could be a climb, it could be descend, or possibly even maintaining our current altitude. This would also be accompanied with an audio alert, which would complement the vertical maneuver. Okay, with the basic purpose and function of the TCAS out of the way, let's talk a little bit more about some of the technical details. The TPA-100, in particular the TPA-100A, is the first of the TPA-100 TCAS processor series, and it was intended to replace the older TPA-81 TCAS processor. So it is a forward fit replacement, and its functions are the same for all practical purposes as a TPA-100A, or the standard TCAS. What I mean by that is we're looking at a 40 nautical mile maximum surveillance range. This maximum range is a function of transmitter power, and that is set by design restrictions, by ICAO, by the FAA, and so forth. We can't go farther than 40 nautical miles because we're not allowed to transmit more power beyond that boundary. One of the reasons for being concerned about limiting the transmit power is that the TCAS will transmit over 100 active interrogations each second. Now we transmit these 100 interrogations on both the top and bottom antennas in the forward, left, right, and aft directions. So it's a tremendous number of interrogations that are transmitted every second. And we have to take certain precautions so that we don't interfere with air traffic control radar, which of course is the more important, if you will, system that we don't want to interfere with. Now, just to stop here for a minute, also point out that in the surveillance volume we have a 40 nautical mile range. TCAS is also looking 10,000 feet above and 10,000 feet below the aircraft. The display, the part that the pilots look at, there's a control switch so they can select, and most control panels have this, your specific installation may not, but many have an above-below normal switch. So in normal position, we're only displaying aircraft that are 2,700 feet above and below, but if we select above position, now we're going to put on the traffic display aircraft up to 8,700 feet above. And likewise, in the below position, we're going to display aircraft all the way down to 8,700 feet below. So one of the things that happens is the pilots sometimes are not paying attention to the ABN or normal below switch, and they'll be expecting to see traffic that is not displayed. It's because the switch is in the wrong position, and therefore the system is written up. So that's one of the ways we can end up with a no fault found TCAS processor. So the B variant, TPA-100B. This particular model is MOPS 7.1 compliant. It has some collision avoidance algorithm enhancements. This is all the software computation inside. It also adds hybrid surveillance functionality. It will reduce the active interrogation rate by using position information we passively receive from other aircraft via ADS-B. Now remember, reducing the active interrogation rate is important because we have up to 100 interrogations a second. So we want to be efficient with our airspace. We have 2 service bulletins depending upon the part number of TCAS processor that you have, which will convert from an A model to a B model. Okay, the TPA-100C. This is the latest variant. It provides long-range active using ADS-B, TCAS surveillance up to 120 nautical miles. So when the airspace restrictions permit, when we're a long way from terminal areas, typically on transoceanic crossings, we can actively interrogate up to 120 nautical miles. Likewise, it's compliant with the ADS-BN functionality, which allows us to passively monitor aircraft up to 250 nautical miles away by listening for position squitter. The service bulletin listed will convert the B model to the C model via software change. Okay, so getting more into the system maintenance aspect, I want to talk about the TCAS antenna. Now this is a special antenna because inside we actually have 4 individual antenna elements. And we use the 4 antenna element scheme during transmission to allow beam steering of the TCAS interrogation. So during the interrogation sequence, we can focus energy to the front quadrant, to the left, right, and to the aft on both the top and bottom antennas. And we do this by applying phase differences to each of these 4 elements during the interrogation transmit. Now, when we're done transmitting and we're listening for the received replies, we're going to monitor these antenna elements and we're going to be measuring for minute phase differences which are occurring between the elements. And it's from these small phase differences that we're able to derive the bearing of the intruding aircraft. A generalized block diagram of the system is shown here, and we can see that the TCAS processor is connected to the Mode S transponders, and the Mode S transponders are an integral part of the TCAS 100 system, and they're supplying the TCAS processor with very important parameters such as barometric altitude and also control unit inputs. So it's important to point out here that if we have any malfunction in the active Mode S transponder, then that's going to cause the TCAS system failure. We have to have functioning transponders in order for the TCAS system to work as a whole. Also shown on the inputs are radio altitude. Radio altitude is a fundamental input. It has to be active continually throughout the flight, and any disruption in the radio input signal will cause the TCAS system to fail. And if radio altitude drops out for a moment and comes back on, then TCAS will recover, but we will log a system fault. Likewise, the pitch, roll, and heading data is needed by the TCAS algorithm to calculate whether the intruder is moving or our own aircraft is moving, which is resulting in the phase differences of the received signal. So again, these are important inputs. They have to be valid, and they're monitored by the TCAS continually throughout the flight. The program pins, they provide a variety of installation-specific information, such as volume setting, maximum number of aircraft that are displayed, and so forth. And the discretes are going to be looking at flap and gear position because we will be looking at that to limit resolution advisory enunciations at certain phases of flight. Okay, with all the system knowledge covered very quickly, let's talk about some of the factors that are just inherent to TCAS which result in a high no fault found removal. Well, TCAS is inherently subject to a high removal rate because it's continually used by the crew throughout the flight regime. TCAS information is enunciated on the primary flight display. Traffic information is continually shown on the navigation display. So any dropout, even momentarily, will be noticed by the crew and written up. Likewise, there are what I call perceived anomalies by the crew. And we touched upon this a little bit already. An example given being the above-below normal switch, which is simply determining what slice or layer of the surveillance volume we're displaying for the crew. But again, it's easy to be disoriented with what the control settings are, and it's common for the crew to misinterpret these settings. So if they think they should be seeing an aircraft and it's not displayed, that can be a maintenance write-up. If they do see an aircraft and it isn't displayed, that may also be a write-up. And it's important to point out that TCAS is going to search the surveillance volume, it's going to pick the most important aircraft to display. So if TCAS deems this aircraft is not important and we have a limited number of aircraft via PIN programming that are displayed, then TCAS will not display that aircraft. So I just wanted to touch on that momentarily, that it is common for the crew to write up TCAS because of these perceived defects. The other point, TCAS depends on continuously valid data from other systems. And as I mentioned before, any loss of data, even if it's momentarily, will result in a TCAS flag shown on the displays. The next point from my experience with TCAS is you really have to be cognizant of the RF cabling in this system. Again, I stress TCAS is an RF communication system with 2 antennas and 16 antenna coax cable connections. You have antennas, you have 4 cables going out to the top antenna, 4 cables going to the bottom antenna, and you have connections on both ends at the TCAS mounting tray and at the antenna itself. So you have 16 connections, and anyone working with RF systems knows that any place you have a connection, there's a potential for a maintenance issue. Also, the TCAS antennas, they're large, they kind of look like a snowshoe. They're also prone to failures themselves for a number of reasons. One is improper bonding. When you install a TCAS antenna, be sure to comply with the maintenance manual procedures for proper bonding. And it's going to, again, depend on the airframe, so make sure you comply with the maintenance instructions. We need a good bond to ensure the proper RF radiation pattern. And if we have a bonding issue, then we can have deformities in the radiation pattern, and that will result in gaps in the surveillance area. And if there's gaps, then the crew will report aircraft not being tracked, and in this case, it's due to the antenna issues. Antennas also occasionally suffer from water intrusion, especially the bottom antenna, because oftentimes humidity will condensate and will settle in the bottom of the fuselage. And if you are troubleshooting a bottom antenna problem, you'll go out, you'll find an excessive amount of corrosion because the antennas have been in standing water for a long duration. Also, the bottom antenna is subject to impact damage from the nose wheel tire throwing up runway debris. And as the fiberglass shell is nicked and scratched, little cracks form. Again, that's another way for water to intrude and to disrupt the elements in the transmission pattern. Antenna cables are also something to be aware of. They are constantly expanding and contracting due to temperature changes. They can be compromised by corrosion and so forth. So be aware that the cabling is an important aspect, maintenance aspect of the TCAS system. All right, so what are some tools that we have available to help us effectively troubleshoot TCAS systems? Well, the most fundamental and useful tool is the front panel display on the TCAS processor. We have a service information letter written that will describe the use of the front panel, also a very helpful video that is referenced in that SIL. And I encourage you to go to our technical publications online, download that pub, watch the video, and just have that on hand. It will show you how to perform a TCAS system self-tests and how to determine if a fault is a processor fault, in which the processor would indeed need to be removed and replaced, or if it's a system fault. which calls for us possibly replacing a radio altimeter. If you're struggling with intermittent faults on a particular aircraft, there's also a very useful fault history that can be brought up and read that will show you, the history of different faults that have occurred within the system as a whole. The next tool that we have available is our TREX, or TCAS Recorded Event Transcriber tool, which is a PC-based software which allows us to analyze data that is downloaded from a TCAS processor using a PC MCIA card. So we're able to download the fault history, take it into our desk, or look at it with a laptop, and print it out, save it, archive it. It's just a convenient way to look at the history and to keep track of what's occurring on a particular aircraft. Again, we have a service information letter that goes into detail on acquiring and using the TREX tool. So I encourage you, again, to go to our tech pubs and take a look at that. This will show a graphical picture of once you have the TREX installed on a PC and you're looking at the recorded information. You can see the flight legs, the faults associated with the flight legs, and so forth. So it's somewhat intuitive. So the last thing, well, almost close to the last thing, second to the last thing I should say, that I want to talk about are some of the service bulletins that we have released that will have an impact on No Fault Found. We have Unit Mod 2 that corrects a transmitter-associated faults. These, if you look at the TCAS fault report on TREX, this would be flagged as a TLVL fault. This mod can be performed on an attrition basis. Likewise, Unit Mod 3, it's associated with the receiver. It reduces parasitic oscillations, and it is also installed on an attrition basis. Unit Mod 4, this is associated with ARINC 429 inputs from other systems, such as a radio altimeter if it's ARINC 429, or an ADRU if it's an ARINC 429 type ADRU. And these reduce intermittent faults due to noise or bad data inputs on the ARINC 429 bus. Unit Mod 5, it prevents receiver calibration and transmitter faults. And just one thing to mention, as TCAS is flying and as it's operating, the system continually calibrates itself to adjust for changes in antenna cable length and so forth due to thermal changes. So it's a very active RF system. And again, Unit Mod 5 will enhance the receiver calibration and transmitter power faults. Unit Mod 6 is also associated with the transmitter, and again, it will impact the TLVL faults. So last, in summary, just some recommended practices to reduce no fault found. First, number one, don't remove a TPA-100 without first performing the system test. You need to run that test. You need to see why it is actually failing, because it may be one of the contributing systems. Next, use the front panel or TREX to review the fault history and examine for any intermittent faults that may be occurring. So look at the history of system performance. Third thing, check the TCAS mounting tray antenna cable connections for proper spring action. So if you have an antenna related fault and you've been troubleshooting that, one thing to keep in mind is on the mounting tray, the TCAS processor mounting tray, the RF connectors, the shields, the round shields are spring loaded. You should be able to push them with your thumb and they will be spring action and they will push back into place. Sometimes because of contamination, those may get stuck as you push them backwards. So you want to make sure that that is a good, clean spring action. And the last thing here, repeated antenna faults are going to require an antenna check. And as I mentioned before, you need to verify antenna bonding has been properly achieved, that you have a good ground plane, because this will affect the TCAS transmission pattern, the surveillance volume pattern, and will also likely result in TCAS antenna